Thanks, Kieran. So what I'm going to talk about is focused on the core-mantle boundary magnetic field. And I'll try and say what I think we currently know regarding the core-mantle boundary field and what the frontiers are for trying to go further, in particular, the opportunities with MSS-1. But to begin with, before going to the core-mantle boundary, I thought we should start by looking at one of the main targets for the MSS-1, which is the South Atlantic anomaly. So what's shown here is the intensity of the magnetic field at the Earth's surface during the time when SWARM has been making measurements, so using data up to the end of August this year. So what you can see is the region of weak field intensity in the South Atlantic has been growing, not just centered on South America, also very noticeably just to the southwest of Africa. So the question, of course, is, well, what's responsible for this? What's the origin of this? So to answer that question, we have to go down to the source of the core field at the core-mantle boundary. And there's a slight complication there, and that's that we can only access the large-scale part of the core field because beyond spherical harmonic degree 13, we have the lithospheric field also involved, which is shown in this power spectrum of the magnetic field as a function of spherical harmonic degree on the left side. So if we just do the usual thing of taking the field up to spherical harmonic degree 13 and plot it at the core mantle boundary, we get the picture shown on the right side here. So orange is radial magnetic field coming out of the core, blue radial magnetic field coming back in. So what's the origin of this South Atlantic anomaly feature? Well, you can see that there are reversed flux patches, so blue in the orange hemisphere here in the Southern Atlantic. And there's also a lack of strong normal flux, so that would be orange in this hemisphere. So if you want to understand the South Atlantic anomaly, the question really is, well, what's the mechanism controlling the structure and evolution of these flux patches? So what can we do with satellite geomagnetism to try to progress our understanding of these things? Well, as I see it, there's really two frontiers here. So we could either try to go to higher spatial resolution to look at these features in more detail. So there we have a problem. The crust, the lithosphere is in the way. So just using a potential field approach alone without any additional information, we can't go further. And secondly, so I'll come back to some ideas about how to get past that. Secondly, we'd like to go to more rapid time variations of the core mantle boundary field. So to try to go down to timescales of 1 year and below. And there, the problem is contamination, leakage of magnetospheric and ionospheric signals into our core field. And this is really limited by, at the moment, by SWARM's local time coverage, which is between 4.5 and 9 months, depending on the arrangements of the satellites. So I'll now try and give some thoughts from my side about how we could try to make progress here. So I've done some work together with a PhD student in DTU, Mikkel Ottsen, where we've tried to build a separate model of the core, the time-dependent core field and the lithospheric field. So we parameterize with spherical harmonics separately the time-dependent core field and the lithospheric field. And then we use some prior information based on the expected structures that we expect, on the one hand, from the core field. So looking at a collection of realizations of dynamo core fields, we've derived covariance functions for the core field. And similarly, looking at many simulations of the lithospheric field, varying the parameters that goes into these models, we've derived covariance functions for these lithospheric fields. And based on these covariance functions, we can decorrelate the radial field at the source. So either at the Earth's surface or at the core mantle boundary. And so we can write the magnetic field in terms of decorrelated variables X. And then we estimate field models where we minimize a cost function consisting of the fit to the data and then some measures of the information entropy separately for the lithospheric field and the core field, where built into these is the depth of the sources and information on their covariance structures. So I'd just like to show the results of that. So this is the type of map that we can get by this approach. Now this is we're able to go out to spherical harmonic degree 22 at the core mantle boundary. So you'll see more small scale details compared to the map to degree 13 that I showed you earlier. So that's in 2006. And when we had good data from low altitude from CHAMP, and then this is during the SWARM era in 2019. If I flick back and forward between those, you'll see that there's field concentrations at low latitudes, which are coherent and they're moving westward with time. And what's, I think, particularly interesting for the South Atlantic anomaly is these reverse flux features are kind of split, and they always go along with a strong normal flux patch. And this is what you would expect, I think, with flux expulsion out of the core. So this is interesting. And another interesting point is if you look within the reversed flux patches, we can see motion within the reversed flux patches, not always going westward, but also eastward. So I think this is a first step in this direction, but maybe this is a possibility for trying to attack going beyond this barrier of the crustal field. So some remarks regarding the structure of the internal field. I think some possibilities here. So if we think about the orbits of MSS-1 and SWARM that's already been discussed about, we see that there are these interesting close encounters, as Niels calls them, or crossings. And this is rather similar to what happens in aeromagnetic surveys where you have tie lines going across them. So I think there are definitely possibilities here for trying to take out systematic errors along the tracks in each of these satellites to do a better job regarding the crustal field. And then, of course, also with the, I'll try and go back here. Oh dear. Also regarding the crustal field, I think if MSS-2 comes, that would be the major step forward coming down to low altitudes. And as Niels already mentioned, I think a key thing there is to make sure we try to do the best job we can during solar minimum when the disturbing currents are less. Regarding, I think there's also a possibility here for collaboration between dynamo simulations and studies of the core dynamics. So an interesting thing is how often do these simulations produce things like the South Atlantic anomaly? And at least for standard dynamo simulations, they struggle to do this. So here's two pictures from two rather advanced dynamo simulations, very low Ekman number. And these do produce reversed flux patches, but not systematically. The reversed flux patches are usually either inside the tangent cylinder at very high latitudes or close to the equator. So a question is, what are we missing in these models? Why do they not regularly produce things like the South Atlantic anomaly? So I think there's some feedback between the observations and the simulations, things still to be understood on that side. So I'll now move from the spatial challenge to the temporal challenge. So what's shown in this movie is the second time derivative of the radiomagnetic field. So that's the acceleration at the core-mantle boundary, again, over the time when we've had swarm data. So what you'll see is some rather slow changing features at high latitudes and a lot more dynamic changes at low latitudes in the Pacific region. And these things that you'll see within the Pacific region, these are the origin of the waves signal that Nicolas presented before. So the question is, can we do better with the kind of temporal details of the core-mantle boundary field that we could think about retrieving? So the limitation here at the moment is when we build these field models, these are typically parameterized in terms of splines, and we minimize the time derivatives, high-order time derivatives of the radiomagnetic field at the core-mantle boundary. And when we do that, we smooth things very much, especially on short length scales. So when we do that, in fact, we're filtering out information that could be of interest, especially for the waves that Nicolas was discussing. So you might ask, well, what happens if you just regularize your model less? Well, so we've done some experiments recently with Clemens Kloss in this direction. And what happens is your core field becomes polluted by external and related induced signals. So that's telling us we need to do better with our models of the external field. And these external fields at the moment, they're really limited by the rather low local time coverage of swarm. So this is the opportunity to do better if we can do better with our external field models. And here I was just making the point that's already been made several times, that with this very rapid local time coverage of MSS-1 in the gold bands, within 30 days, we're sampling all local times. So this means we could think about more updating models of the ionospheric field and magnetospheric field on monthly timescales. And if we can do that, then we should be able to go after these more rapid core field signals. A final point I'd like to raise is this thing about we won't have full global coverage because of the MSS-1 orbit, right? So how are we going to handle that? We might have better temporal description of the external fields, but more at mid and low latitudes. So there's a few approaches here. The standard thing would be just to go ahead and build our usual spherical harmonic models and have temporal regularization to try to stabilize things where we don't have sufficient temporal data coverage. But if you do that and you set your regularization to control the high latitude areas, you'll also smooth out things at low latitudes, which is not what you want. So I think there's room here for some other approaches. In particular, I'll mention again the virtual observatories that Nicolas showed, and I think might be discussed later with Will Brown in the discussion area. Another possibility that I've worked on is trying to do some local estimation of the core-mantle boundary. So it turns out that you can write the vector magnetic field at satellite altitude in terms of the core-mantle boundary field, if you know that all over the core, and we know the Green's functions that connect these things. So this means by taking linear combinations of the data, we can construct estimates for the core-mantle boundary field at any location we're interested in. And these estimates are local averages, and they have a kernel associated with them. And we can minimize the difference between this averaging kernel and a target kernel to try to get spatially localized estimates that have as good resolution as possible. And we've done this trying to look at higher resolution of the secular acceleration. This is a time longitude plot, and compared to one of the images I showed earlier, you'll see that there's a lot more detailed structure possible here using this approach, which is really focused on estimates just at the equator. So perhaps this is also a possible option in this way. So I'll finish with my summary. So first of all, from my side, studying the core field, MSS-1 is providing this very exciting new way of sampling Earth's magnetic field in space and time. And in particular, there's exciting opportunities to improve our models of the external field. And that then opens the way to study more rapid time variations of the core field, and then to make progress on the small scale core fields and maybe understanding things like the origin of the South Atlantic anomaly. I think there we have to collaborate with the physics and the dynamo simulations to try to work in parallel on that. So I'll leave it there. Thank you.